So as she already said, I'm a researcher, and I spent most of my life in academia. And I also published a book on advanced data management, including NoSQL databases and cloud databases, and I took some pictures in this talk from this book. And I also organized a workshop, NoSQLnet, where we really want to attract submissions in this data management area, and we also welcome industrial application papers. So that's my background, basically. And I want to give you a very rough overview over this area of NoSQL databases. So I have lots of slides. I will very quickly go through them to really give you this broad overview. You see, there are a lot of topics. So let's start. So of course, the basic clash is that you have these traditional SQL databases, but we also have lots of new data models which are or could be summarized as so-called NoSQL databases. And so this bottom part I will focus on in my talk. And so, of course, the first question is, what do we actually need a database system for? Well, actually, you have lots of data, and you have to manage them. You have maybe huge amounts of data, and you want to be efficient. You have to persist them on disk, and so storage has to be reliable. You don't want to lose any data. It has to be consistent if you have a distributed system. Then you don't want to have duplicates in your data. You want to have non-redundant storage. And of course, you want to have multiple user access. So we see we have lots of requirements towards database systems. And we also have new requirements due to the modern data structures. So we have, for example, complex structures like social networks. We have frequent updates on the data, lots of writes. And also we have this distributed storage. So we have the cloud storage or something like this. Okay, so we see actually the ideas behind NoSQL databases are quite old. There are very old scientific papers on it, but now we see that actually this is a revival of these non-relational data models for novel applications and also on this novel hardware that we have nowadays. Yeah. So as I said, I will give you an overview of these data models. Let's start with graphs. So why do we need graphs, or what could be stored in graphs? For example, you could have social networks where the nodes are the persons, and you have some relations between the nodes that would be the edges between the vertices here. Or you can have geographic information systems where the nodes are the cities, and on the links you have some information like the distance between cities and so on. And so the basic data model for graph databases is what is called a property graph. And property means you have this kind of key value pairs in the nodes and along the edges. So every node and every edge should also have an ID as a key value pair. And then you can store additional information by adding more key value pairs to the nodes and the edges. And actually, I think most of the graph databases also support typing. So you can give each node a type, for example, a person type. And the type information for edges is usually called a label. So you can also have different kinds of labels along the edges. So what's usually not allowed is that you have duplicate edges with the same label. So labels should be unique between any two nodes, between any pair of nodes. Yeah? And of course, now when you want to work with the data in this graph database, in the graph, the basic notion is that of a path. So you somehow navigate by going from one node to the next. And so you have a path, and you can find your data along paths in this graph. Now let's have a look at open source systems that are available. So one library for graph management is Tinkerpop. And it's actually an Apache project where you have lots of modules which you can use for graph processing. And then the biggest open source database for graphs is Neo4j. And they have a very nice query language to interact with the graph database, which is called Cypher. And here in the example, you see that you can really, you can start with some node. You can look up a certain node, for example, with a name property being Alice in this graph. And then you can, with this match statement, you can navigate along a path in this graph, and then you can output some node. But there's also a more advanced data model for graphs, which is called here a hypergraph, and there's also a open source graph database called HyperGraphDB that really implements this model, and this graph model means you can have hyper edges in the graph, and that is, you cannot just combine two nodes along an edge, but you can have more than two nodes in one edge. So that was the very short overview of graphs. Then, of course, we know XML. It's a very established standard in this case, and we have this kind of nesting. And some would say, okay, that's a bit old-fashioned, why do we need XML? But seriously, there are a lot of legacy applications that still use XML, for example, in configuration files. And the nice thing is that it's really a standard, and we also have standardized query languages like XPath and XQuery. So as you may know, an XML document can be represented as a tree, like, for example, this small snippet of a hotel or reservation system for hotels could be represented as a tree. And very important for XML data is how you number the nodes. So how can you really traverse in this tree by giving some nodes to the numbers? And if you have modifications of your data, the question is, when you modify some data, how many nodes really have to be renumbered regarding your numbering schemes? And there are also two open source XML databases on the market, and they have nearly the same features, but as I put here, the numbering schemes are a bit different. So one is ExistDB and the other one is BaseX. Okay, then let's go to a more simpler data model, which is the key value store. So usually a key value store would store key value pairs, and the basic operations are that you store some value by putting a key and the value into the store, into the key value store, and you can then access data by retrieving it via the key. So you get the value by calling some find function on the key. And you can store a value by the key. So you see, that's a very simple data and interaction model. So it's a simple data structure. You don't really have an advanced query language. So it's actually good for data-intensive applications. Yeah? And you might know the biggest open source systems on the market currently. That's Redis. And Redis really supports more advanced data types than arbitrary binary values, so you can have strings, linked lists, unsorted sets, sorted sets, hash, bit array, and a probabilistic data structure called hyperloglog. And we also have Riak, the Riak key value store. And you group these Riak objects into buckets. And Riak, they recently implemented these convergent replicated data types, which helps you when you have concurrent accesses on the same data. And you have a search functionality based on Solr. Okay, then we have heard of MapReduce. MapReduce really works on these key value pairs in general. So actually it was a Google, let's say, invention. Yeah, so some Google guys published this paper at the conference. And we have seen this. So you can, the nice thing about it is that you can process data in parallel. So you have some input that you split into parts, and then you have this map function which does some computation in parallel on several servers on this input. Then you have some coordination phase, which is called shuffle, where you regroup the data, and in the end you have some reduce phase, which you can again run in parallel to compute the final output. So a very nice thing, again, for data-intensive applications. And for this MapReduce, we've heard that in previous talks too. We have Apache Hadoop, and we've heard of other creatures in this universe of Hadoop, like we have heard about Spark 2 to make this data programming a bit more flexible. Then we have something like Pig or Hive as different kinds or methods to interact with Hadoop, really. Okay, now the next topic I want to touch on is JSON, JavaScript Object Notation. That's kind of a recent data format. It's deemed to be more human readable than XML, and it's also more compact than XML, but it still allows you to nest key value pairs. So it's basically a nesting of key value pairs. And these so-called document databases, they are mainly, or their purpose is mainly to store this JSON data, right? So when you hear the term document databases, it usually refers to storing JSON data in JSON format. And there we have very successful open source systems. MongoDB uses a sort of binary representation of JSON, and it has a very nice a JavaScript-based query language. So for example, when you access the database, you can just call this find method and put some conditions into the brackets and so on. Then we have CouchDB, and CouchDB really uses this map and reduce framework to retrieve data. So whenever you want to access your data, you have to define your view by defining this map function, which could, for example, look like this. And then, as like say a successor of CouchDB, we have also Couchbase, and Couchbase has a SQL-like query language on top of this MapReduce framework. So let's talk a bit next about column stores. Well, so actually, when we talk about SQL databases, we usually think of row stores, where you really store the data in row-wise fashion. So you go from one row to the next, and you store it consecutively on disk. But column stores are organized differently. They go column-wise. So you store data column by column. So what are the advantages? Well, actually, you can really, just focus on the data in one column. So if you focus on one column, you just have to read these data from disk. And the nice thing is that the value, the data type in each column is unique. So you can really work on that data. For example, you can compress them. So you have a lot more compact storage when you have a column store. And of course, you can also iterate or aggregate over these values. And you can easily add new columns to your store. So talking about compression, we have several options that are also really implemented in modern column stores. I will only focus on the first one, which would be run length encoding. And run length encoding means that you look at the value, and then you say, okay, for example, the value 225 starts at row 1, and then you have 3 repetitions of the same value. So you just have to write a single tuple for these 3 repetitions. And then you say, okay, in line 4, we have the value 347, and then we have 2 repetitions. So run length really describes how often a single value is repeated in this column. And the nice thing about it that you do not have to uncompress or decompress the data when you want to answer queries. You can just run, for example, a count query on these data, and you just you sum up all the run length of the individual occurrences of this value, and there is your result. Okay, then we also have some open source systems here. For example, MonetDB. So as far as I know, MonetDB is the only open source column store system, but it's there for decades. So it's really an established system. And then we have Apache Parquet that implements the so-called column striping algorithm. So it can transform nested data, for example, in JSON format, into column representation. A very nice invention. But this column-oriented storage is also interesting in commercial systems. For example, for HANA and Vertica, they use this column-oriented storage model. Okay, and then a more advanced or flexible data structure is this so-called BigTable data model. And there you have a very flexible map. So you actually index your data by a row key, by a column key, and a timestamp. And the nice feature about it is that you can have your columns grouped into sets. And these sets are called column families. Yeah? And at runtime, you can easily add more columns to one column family. So for example, when we have a library data table, we can have the book ID as the row key, and then we could have 2 column families, one for the book information and one for the lending information. And you see here that for example, title would be a column name, and databases would then be the value. So you can flexibly add this column and value pairs to the column family. And what you can also see is that not all rows have to have the same column. So we really have a very flexible data model, and the columns can be changed from one row to another. Okay, and not only from the data model is this data type very interesting, but also from the storage management, because we collect here the recent data in a memory table, and then we flush this memory table to disk, and after that the files will never be touched. They are immutable. Yeah, so we have just something like an append-only storage for these data base systems. But of course, we have some disadvantage with this one because we might have to read in to identify the most recent write. We might have to read in data from different files. Yeah. So then you have to combine the writes for a single row key in the memory before you can really identify which is the most recent value that was written to disk. We have some open source systems. The most famous ones are Cassandra, that stores column families in a key space, and it really has a nice SQL-like query language, which I think makes it more easier to use than HBase. And HBase would be the competitor, which stores tables in namespaces. Yeah? And then you can have column families inside the tables. So yeah, so my personal opinion is that HBase is not so nice to interact with because it doesn't really have this nice query language. Okay, and then as the final topic, I will talk a bit about polyglot persistence, because you have seen we have lots of data models. And what database should we actually choose? That's the big question here. And well, one answer would be you can choose as many databases as you need in your enterprise and in your application, and then you have to combine it. So you would usually have an integration layer that can access the different database systems, and there's even an open source system called Apache Drill that can connect to different databases and combine these results. So let's show this graphically. Like, for example, we can here have such a polyglot persistence layer that integrates all the functionality that you need, and you can access it with different kinds of queries that you have. And below, there are different kinds of databases connected to the system. Then there's something called the Lambda architecture, which is really for streaming data or real-time data. And there the question is, well, how can you really manage this stream of data, this continuous stream of data? And yeah, there's also one open source implementation called Apache Druid. So if you're interested in this kind of technology, so here you see you have one batch layer which really collects the historical data, the established data, and then you might have some serving layer that can compute some indexes over these old data, and that takes some time. So in order to manage the newly arriving data, you also have a speed layer that collects the most recent data. And so when you have some user that wants to interact with the data, you have to merge the historical data from the serving layer with the new data from the speed layer. So that would be the idea. And so my last topic would be multi-model databases. Here you have a database that offers you different APIs. Yeah? So actually you have a single database system, but you can have different access methods and different data models in this single database system. And like two open source systems. One would be OrientDB, which has a document API, so JSON API, an object API, and a graph API, or a RungoDB, which has a graph API, a key value API, and a document API. So they are really competitors in this area. So the idea is you have like a single database system and a single database engine, but you might have different API layers on top. Here, for example, you have a key value store, and you have a graph layer on top, and you can access also by using graph queries and can access your data and manage your data with this API. Okay, so that was my talk. My conclusion is we have many, many data models, so we don't need to consider only relational tables. We have lots of different query languages, which is really a problem because in this NoSQL area we don't have any standards yet. They might come in the future. Of course, because if you look at the open source systems, you might have problems with reliability. You don't know how long the system will run or whether there will be long-term support. And in the end, well, you have to really look at your application and your enterprise and identify which database system you need and then decide what's the best for you. Okay? So thank you very much.
Thank you very much.